Hello everyone, I welcome you all to this class. This is the linear algebra class, and today we have this proposition on the board here. We want to prove this proposition. Under this topic we introduced in our previous video, similarity of matrices. We saw the definition of a similar matrices. So let's look at this proposition. They say that if two matrices are similar, they will have the same determinant and they will have the same eigenvalues. So we are going to prove each of them, right? So let's start. So let's prove each of the proposition. So let's start with the first proof. The first one. So we want to prove the first one, right? Okay. I say let A and B be similar matrices, right? So because I have said that let them be similar matrices, then you must find an invertible square matrix P such that the inverse of that P multiplied by your matrix A multiplied by P will give you your matrix B. So this is the definition of similar matrices we saw in our previous video. Then determinant of B will be equal to, let's evaluate determinant of B, right? So B is this. We want to find the determinant of B now. Determinant of B will be determinant of, what is your B? B is the same thing as P inverse multiplied by A multiplied by P, right? As we saw it here. So this will be equal to determinant of a product is the product of their determinant, right? So this determinant of P inverse then multiplied by determinant of A then multiplied by determinant of P, right? This will be equal to determinant of inverse of a particular matrix is the inverse of the determinant. So determinant of P inverse is the inverse of determinant of P. So determinant of P. So this is what it will give us, right? Then multiplying determinant of A, then multiplying determinant of P, right? This is a product, right? What do you notice? This can divide this, right? So what do you have left? So what I have left is determinant of A. So where did we start? We started from determinant of B, and we're ending with determinant of A. So this simply implies that determinant of B, we have it here is equal to what? Determinant of A. So with this we have proven the first proposition, the first one. So let's look at the second one. What I have written down here is now any eigenvalue of A will satisfy its characteristic equation, right? That is determinant of A minus lambda I will be equal to what? 0. So what I have written down here, I say now any eigenvalue of A will satisfy its characteristic equation, right? And this is true. If you find the eigenvalue of, if you find the eigenvalues of a particular square matrix, then each of the eigenvalue will satisfy this characteristic equation, because it is this characteristic equation you used to find the eigenvalues. So it will satisfy this same characteristic equation, right? Now, for us to show that these two matrices A and B will have the same eigenvalues, I will show that they will have the same characteristic equation, because if they have the same characteristic equation, it means that their eigenvalues will be the same thing, right? So let's write down the characteristic equation of your matrix B and show that it will be the same thing as the characteristic equation of your matrix A. So 0 equals determinant of B minus lambda I, because this thing will give us the characteristic equation of what? Your B, right? This is the characteristic equation of B. So this is equals to determinant of, we have written down something here before, that your B matrix B is equals to P inverse AP, right? So I'm going to replace this B with P inverse AP, because A and B are similar, right? So B is the same thing as P inverse AP, right? Then I'll have minus lambda I, isn't it? Then this will be equal to determinant of, I have P inverse AP minus lambda. Because I have P here, I want to get something in terms of P here so that I can factor it out. So I'll write this my identity matrix as P inverse P, because the inverse of a matrix multiplied by the matrix will give the identity matrix, right? So the identity matrix is equivalent to P inverse multiplied by P, right? So with this, I can factor out P inverse from the left, I can factor out P from the right. So this implies determinant of, so what I will do, if I factor out P inverse from the left, I have P inverse, then I have open bracket. What I will have now is A, then I have minus lambda I, then I'm factoring out P from the right, P. What I did is that I factor out P inverse from here, from the left, and I factor out P from here, from the right, right? If you factor out P here and factor out P inverse here, what will remain here is your matrix A. If factor out P inverse here, factor out P here, what will remain here is lambda, right? But you cannot be subtracting A and lambda, because lambda is a constant. You can't subtract a matrix and a constant. So you have to multiply the lambda with the identity matrix. So it will be A minus lambda I instead of A minus lambda. Do you understand? So now I'll use the property of determinant. So this will be equal to determinant of P inverse, because the determinant of product is the product of the determinant. Determinant of A minus lambda I, determinant of P, right? So this will be equal to determinant of inverse of a matrix is the inverse of the determinant. So this is inverse of determinant of P, right? Multiplied by determinant of A minus lambda I, multiplied by determinant of P. So with this, something can divide, because I have determinant of P here at the denominator here. I have determinant of P here. So this can cancel this. So this can cancel this, right? So what do we have left? What we have now is determinant of a minus lambda I. That is what we have now, right? So this is what we have now, determinant of a minus lambda I. So we started from where? 0 is equal to determinant of b minus lambda I. And this determinant of b minus lambda I is giving us the same thing as what? Determinant of a minus lambda I, right? Which shows that determinant of b minus lambda I is the same thing as determinant of a minus lambda I. So 0 is equal to determinant of b minus lambda I and is equal to determinant of a minus lambda I. So this shows that what? Their characteristic equation is the same because determinant of b minus lambda I is the same thing as determinant of a minus what? Lambda I. So it's the same characteristic equation you're going to get. So the same eigenvalues.